Up a little bit. Okay, here we go. It's like my lawnmower when I was in high school. Oh, that was good. There we go. Come on. It's going pretty good. All right. And we'll cool the cold side down. I don't know. I couldn't really tell that much difference. It is speeding up. I'm trying to slow it down now by warming up the cold side. Yeah. Let's try now. Let's cool this thing down. Yeah, it's hard to tell. Let me get it on the end here. I catch my bag on fire. It's like that electro boom. You ever see that YouTube channel? The full bridge rectifier. Okay, so that's the Stirling engine. We tried to play with a little bit on the cold side. It wasn't as dramatic as I thought, but still, pretty neat little engine. You can see the hot side on the right, cold side. The pistons are just like 90 degrees to each other on the crank, and we'll talk about that when we get into the indicator diagram. This little belt is driving a electric generator, and the generator is generating enough voltage to light an LED. So, all right. Take away the heat, and it's pumping that heat over to the cold side, and when the temperatures get close enough to each other that you really don't have a differential, then the efficiency of the engine drops. Yeah, we have friction losses obviously because that's what the squeakiness is, and there it goes. So that's the Stirling engine. Love those things. You can find that on Amazon for a reasonable price.
Did it come with a fancy light? Or did you
Yeah, it came with the fancy light. Yeah, so that was part of the package. It's kind of fun. So yeah, I'll probably put a link in the description for the one that I bought. So how's that sound? Okay, so let's look at the state variables table for this Stirling engine. It's not so easy when you have an existing engine to figure out, all the parameters for the state variables. We know we probably have some kind of diagram like this for the PV diagram, the indicator diagram, so that you can generate, the numbers that are related to the amount of work. We have, the way this works is both pistons push out and then come together. So there's two pistons, but we have one chart. And so we'll get into how the pistons work with the expansion and the compression, okay? But let's try to figure out the dimensions of our engine. So I've taken this ruler and I've looked at this distance here on the crank, and that's the stroke of the piston. So from one side all the way over here is the stroke of the piston. That's how far it moves in and out. So that's S. So the stroke of the piston is about 12 millimeters. And the diameters of the pistons, I tried to estimate, well, the piston, when it comes out of the little sleeve, I can measure it with the micrometers, and it's about 12 millimeters. So the area of that piston is 226 millimeters squared. So just using, 2 power squared. and then we have the stroke, which is 13 millimeters. That's that crank distance. And so then you take that stroke times the area, and that's how much volume this piston is sweeping out. And that's going to be the difference between C and A, VC and VA. Those are your two volumes that you always need to know for these engines. It's the volume at point A and the volume at point C. So that's something that you can remember for all of these engines. C is the largest volume and A is the smallest. So when the pistons are all pressed in, that's VA, and when the pistons are all pushed out, that's VC. So that's our difference. The stroke times the area of the piston, that's our difference. It's about 3 millimeters. Okay, which makes sense if you look at those pistons. You add up the two little volumes, it's about 3 millimeters of displacement. Not a lot. Okay. Now the minimum volume, VA, is not exactly intuitive. We have about, if you look at the pistons, the way they're set up, both of them are not compressed all the way at the same time. One is compressed and the other one is about halfway there. And then they kind of exchange places where the other one's compressed all the way and the other one, the first one's halfway out. And then they move out to where one's all the way out and one's halfway all the way out. And then they swap places where the second one's all the way out and the other one's halfway. So we have about a half a stroke of volume, that's our minimum volume, plus the spherical tip of each of the pistons. So we have that spherical tip times half of the stroke length. That's our smallest volume. And I did this just by inspecting the way the pistons work. Okay. So you could probably do the same if you were looking at it. This isn't anything that I'm not gonna like give you an engine and say, all right, determine these things. I'm just saying, walk with me as we figure out this machine. Okay. So I was looking at the pistons and I said, all right, that's the minimum volume, is this half of a stroke and the spherical tip. So we know that the radius is 6 millimeters, and so we can figure out the volume of that tip, and that's 4/3 pi r cubed. And so we have the radius of 6 millimeters cubed times 4/3 times pi, converting that over to liters. So we have a tiny little correction of about 1 milliliter in those tips, and then we add in that half a stroke length, and that's our minimum volume VA. So that's about 2 milliliters. I'm just keeping all those extra decimals just as guard digits for our calculation. But it's about 2 milliliters. And then our difference, VA to VC, is about 3 milliliters. So our maximum volume is about 5. And so the VC plus the difference will give us that maximum. I think that's a mistake. It should be VA plus the difference from VC. So this right here should be an A, because that doesn't make sense. This is A. So that's the maximum is 5 milliliters, the minimum is 2 milliliters, and the difference is 3 milliliters. So that's that volume displacement. So now we have at least the volumes worked out. We don't have the pressures, but we have the volumes. So that's a start. And we notice too that when the first piston's pushed out and the second one starts to push out, the first piston starts to come back in a little bit. So from piston 1, the hot piston, being all the way out, to the piston 2, the cold piston, being all the way out, there's a constant volume there because they're just exchanging places. And so our constant VB is as big as VC. So the hot piston's pushed all the way out, then the cold piston's halfway there, and then they trying to change places. And so that volume is the same. What's happening there, though, is that hot volume is being pushed over to the cold side. Okay. And then once it's cold, it's being pushed back over to the hot side. So that compression is the cold air being pushed back into the hot side, and then the hot piston compressing it. So let's go back. Let me just draw that on here. So we have the hot temperature. I'll say, how do I want to label this? I can't use P for piston because P is pressure. How about cylinder 1? Is that cool? CYL 1 pushes out here, and then it's at max. Let's just say right about there. max. Okay, let me start over. That didn't go so well. So let's talk about the hot cylinder and the cold cylinder and the displacement volumes in the Stirling engine. So what I did in class, we're going to delete. And sometimes it just takes a little reflection to understand what's going on. Let's talk about the hot cylinder. Okay, and so I'm going to call that C hot. Okay, let me start the PowerPoint to get the pin active. So I'm going to have C hot. So that's the hot cylinder. And this point here at VD is its minimum volume. So that's minimum for C hot. And then as that gas heats up, it goes through half of its displacement and then all the way out to its max value. So that is the hot cylinder being pushed out by the hot gas. Now this volume here is the same because we're actually pumping gas from the cold cylinder over to the hot cylinder at this point. So here the cold cylinder is at its minimum. Let me change pin color. How about that? And so we'll click that. We'll get a blue for the cold. And so C cold is at its minimum right here. And so it's being pushed out to 1/2 of its value, and then here it's max. And so the minimum value for C hot starts here. It's halfway extended, and now it's maximally extended. And so then the cold cylinder starts to take some gas away from the hot cylinder here and ends up at its max here. So from here we have the hot cylinder going from max down to 1/2 of its volume. Oops. So it's going down to 1/2 of its volume here, and then it's all the way back to its minimum here for the hot cylinder. I should have changed my pin color on that one. So this is red. So this is the compression cycle for the hot cylinder. It goes from max to min here. And so back to its minimum value. So that's the extension for the hot cylinder. So it's heated up, it's pushing, that's the power stroke, and then this is the compression stroke. And then for the cold cylinder, we have here from its max value, it starts to take, it starts to pump some of that air back over to the hot side as it's compressed. And so this is pumping from the hot air into the cold side. This is all on the cold side, and then now that some of that air is being converted back over to the hot side where it starts to heat up with the candle flame. And so you can see the different min-max points for the cold cylinder in blue, the min-max points for the hot cylinder in red. And these isochores are when you're substantially pumping, in this case, you've got a half-filled cold cylinder pumping the air over to the hot side until you have a half-filled hot cylinder. This is the low end, so that's the smallest volume. And then over here is the largest volume, where you've expanded the gas and started pumping it over to the cold side. So you've pumped it over to the cold side, and now you have the heat being synced onto the cold side of the Stirling engine. And you can see those two cylinders down here. All right, so that's a correction to what I did in class, and hopefully that'll clear things up for you. Thanks. All right, so then let's look at the state variables table. So we have our volumes, but we need to make some assumptions with some temperatures, because you can't know the pressures unless you know the temperatures. So this is what we've got so far. These were our physical measurements for VA and VC. And we know that VC is the same as VB. And we know that VC is the same as, or VD is the same as VA. So those are easy to calculate. Then we have an assumption. I mean, I was touching the cold side and it really wasn't any different than room temperature that I could tell. And you could even get the thermometer. I had the laser thermometer out with this a while ago, and then I tried it with the thermocouple, and it seemed like the thermocouple was easier to stabilize. So put the thermocouple on the cold side, it really wasn't that different than room temperature. So we'll say that's room temperature. And then the hot side, well, this again, we'll assume too, since these pistons are not airtight, that while it's sitting here on the bench, the gas at rest on the cold side is 1 atmosphere. So it's at equilibrium with the atmosphere, and then we get it started. So that's an assumption as well. And so then we could calculate the number of moles of gas we have in here. Now it's a mixture. So it's a mixture of nitrogen and oxygen and maybe some moisture in there, but for the most part it's nitrogen and oxygen. And so it's a diatomic. So when we get to CV and so on and calculating the work, we will use CV for a diatomic. Okay. And so that's going to be the same moles of gas because they're our working fluid. It's sealed enough that that gas stays in there and is doing the work. If it leaks a little bit, then it just gets less efficient and there's fewer moles of gas in there. And so that's going to drop the pressure, and so you're going to get a less efficient engine if it's leaky. Okay, so this is all pretty simple, just on that assumption of the low side being room temperature. Okay, so then we can measure the hot temperature, and so the hot temperature will be measured as we'll see later with the thermocouple. And then once we know the hot temperature, that's the same temperature as B. So here's another thing too, in these cycle problems that people mess up all the time. Look at the volumes that are the same and the temperatures that are the same. Notice it's the volume B and C that are the same, but look at the temperatures. B and A are the same. Do you see that? That's a place where people mess up. The high pressure lines are the same temperature and the low pressure lines are the same temperature. Those are isotherms. And so A to B is an isotherm, same temperature. And C to D is an isotherm. So that's the same temperature. If you get those temperatures mixed up, all your work values are wrong, all of your calculations are wrong. If you get the wrong temperatures lined up in the state variables table, then you've messed up. And then the volumes, in this case, since we have an isochoric process, the volume of B and C are the same and the volume of A and D are the same. In the Carnot cycle, which we'll do next, like next lecture, we use adiabatic relationships to connect those volumes. And so now for the pressures, we have all three of the 4 state variables, and so we could calculate the pressures with the ideal gas law. Okay, so that's straightforward. So we had to make an assumption with the temperature or measurement, and we calculated the physical properties of our pistons to get the volumes, and then we used the ideal gas law to get the pressures. So it's not too bad. So let's put some numbers into this. So here's our numbers. The color coding here, the orange is assumptions, and then the green are measurements. And so I used my thermocouple, measured the temperature. We measured the volumes with our calipers. So we got the physical dimensions of the pistons, and so those blue things are measurements. Everything else is calculations. And so here's our state variables table in terms of milliliters, Kelvin, atmospheres, and so on. So if we assume that the cold side was 1 atmosphere, then our high pressure side is about 3.4 atmospheres. It's not too bad, but that's a high pressure. That's what's driving this motor. So let's now look at, using the state variables table, let's look at the isothermal process and calculate how much work is done with each of those pieces. Okay, so we know that the BC work value is 0. Why? So looking at our indicator diagram with the PV or the PV plot, the volume doesn't change. And so you're not doing any expansion work if the volume doesn't change. So no work is done from leg B to C. That's just the transfer of the hot gas over to the cold side. And there's no work done. The cold piston's coming out and the hot piston's going in. And so it's just transferring the gas over to the cold side. And the same thing at D and A, you're just taking the cold gas on the cold piston and transferring it over to the hot piston, and it warms up. And so because it warms up, that's that jump in pressure. But no work is done. So for the equation for this work is that isothermal reversible process. And again, this is an assumption that that's an isotherm, but you've got to make some assumptions. So this would be sort of an idealized case that was an isothermal expansion. So this is the equation that we use. We know the number of moles we got from the ideal gas law, and so then we can calculate this. It's negative 0.66 joules. Now this is per stroke, so it's happening quite, you saw how fast it was going. But this is for every stroke, we get about 0.6 joules out of this motor. Okay. And it's negative, so that means it's doing work on the surroundings. And the surroundings in this case is the electric generator, right? It's spinning that crank, and that's turning the generator, and that's lighting the light. So that's the work that we're doing. And we're getting 0.6 joules per stroke out, but then we have to compress it, and so we have to put in 0.4 joules. So that's not a lot of net work. 0.6 minus 0.4, so we got 0.2 joules for a round trip that's coming out of our system. Okay. That's why we need high RPMs, right? If you want to do anything, you need to run that cycle over and over again very rapidly. So we do have the internal energy change. Notice that the internal energy change for AB is 0 and CD is 0. Why is that? Yeah, delta T is 0 for those. They're isothermal processes. So we know that those entries in that table are 0. So we could take the delta T and calculate the internal energy change from BC. So when we pump that gas from the hot cylinder to the cold cylinder using the pistons, that temperature is lost to the surroundings, and so that drops the internal energy. So it drops it by 0.7 joules. And then when we compress it and then we heat it up with the flame, we put in 0.7 joules. So the round trip delta U should be 0, and it is. Because we went down to temperature and we came back up to temperature. So that round trip is going to be 0, delta U. So that's a nice math check. And so then to find out the heat involved is just delta U minus W. And so we can work our way through this. That's our heat. And so we had to put heat into the system in two places. Heating the gas up from D to A, and then keeping the process isothermal during that expansion. So the gas is heating up when it gets pumped into the cylinder 1, and then it's continually heated as that cylinder 1 expands. So there's two places where heat comes into the system. That'll give us our total heat in. So we add up those two positive values of the heat, and that's our total heat. And so remember, our efficiency is the net work for the cycle. So the sum of that column of work divided by only the positive values of heat, because that's what we had to pay for. I had to, the department paid for that isopropyl alcohol. And so that's what generated the heat. That's the cost. And so efficiency is that work divided by the cost. So there's our total heat in, 1.3 joules. And so our efficiency is 0.16. So this is a 16.6 or 17% efficient engine with our numbers. Yeah, so that's why we're not driving around with Stirling engines, because a gasoline engine, the way they've constructed it, is about 25% efficient. So a Stirling engine wouldn't get as good a gas mileage. Now, but the Stirling engine has some advantages over internal combustion engine. In fact, think about that word I just used. What do we mean by internal combustion? Explosions, but where are the explosions? Inside. What about this one?
Outside.
Yeah, this is an external combustion engine. So the heat is on the outside. Now, why might you want this? You're taking a hit in terms of efficiency. You could use an external source of heat, like the sun, like concentrated solar energy. Okay, let's think about in terms of burning fuel. What kind of scrutiny do we use for our fuel, our gasoline? A lot of times the gasoline is scrutinized, meaning it's regulated, not necessarily for emissions, but also for sulfur content and those kinds of things, for not having any chlorides, gases in it because of corrosion, because the combustion takes place inside the engine. If you have a corrosive gas, then it's going to eat up the inside of the engine. And so if it produces chlorides and so on, then it's really damaging to the engine, and that engine won't have a very long lifetime. This thing, since the combustion takes place outside the engine, you could have the dirtiest fuel source you ever wanted. You could burn leaves and make this engine work. And there are people that have, these little, they're playing around, you can find on YouTube, Stirling engines where they just have leaves and junk wood and everything, and they're using that to generate power. And so, again, you can burn anything or use the sun or some kind of heat source, any kind of heat source, and generate electricity or mechanical motion if you need it. Okay. So this is an external combustion engine. The biggest advantage is that this fuel source can be dirty or can be some other kind of thing that's easy to rig up. It's easy to rig up a reflector and a concentrator for solar heat and point it at that hot side. And so that's, you don't even need to burn anything in that case. So 16% efficient, but you didn't pay for the sun, right? And you're not going to stop it except for clouds. Okay, so it's a great way to use waste heat or heat that you just come by naturally, like the sun. So that's the Stirling engine, state variables table, and the efficiency. Now, we have two temperatures here, and we could calculate the best case scenario, and that would be that would be the Carnot cycle, where we use isothermal and adiabatic changes in pressure and volume. So these adiabatic curves would allow us to get more efficiency out of this engine. And how do we calculate the efficiency of a Carnot cycle? It's just the cold side divided by the hot side subtracted from 1. So this is the Carnot efficiency, is 0.34. So if this were a Carnot cycle with just the flame temperature and the room temperature, we could get 34% efficient out of it. So that would be the best case scenario for these temperature ranges. So that's pretty good. So let's look at the adiabatic processes. So the next set of notes, we're going to shift gears. The next set of notes looks to see how we can get more efficiency out of it. So instead of these vertical lines, we would have adiabatic lines where there's no heat flow, and it would cross over like that. And let's say BC, so we'll have it like coming like this. And so those lines will help us get more work out. And so this right here would be D, and this would be B. And we'll have to figure out how to calculate those. And that's what the next set of notes is. Okay. It's basically taking this and looking at it if it were a Carnot cycle. But we're going to get to Carnot cycle, and that's next lecture. We'll just do the adiabatic processes at the second half of this one. So I've talked about these two different processes, isothermal, reversible expansion and compression, and adiabatic. And so it may take you a little bit of time to understand what the adiabat is doing here, because we have two processes that are curved, and one is always steeper than the other. The adiabatic line is always steeper than the isothermal. And that's because the isothermal line maintains a higher pressure because we're putting in heat. So as it's expanding, it would want to cool, but to keep it isothermal, we have to put in heat so it stays on that isotherm. If we don't put in any heat, the pressure drops dramatically. And so we're getting all the work out, we're not putting any heat in. And so that's where the efficiency comes from. We're saving some money by not having to put heat in to keep it on the hot isotherm. And so if you think about the pressure, if it's at a constant temperature and you look at the ideal gas law and you have the temperature's the same, number of moles is the same, gas constant's the same, then you just have that relationship between pressure, where the pressure final is equal to the pressure initial times this ratio of volumes, VI over VF. But that's if temperature's constant. If temperature's not constant, you could put the temperatures in here, but what if we just want to plot it on this chart? We just have two variables. And so we've got this relationship. If there's no heat flow, then we have this new relationship with this gamma, and this is the big deal. Okay. So that gamma is what tells us how steep this line is. And that gamma is a function of our working fluid. So if we're using air like we have here, which is diatomic molecules, nitrogen and oxygen, we have a different gamma than if we were using helium, or if we're using steam, like hot water. So steam engines will have a different gamma than just air or combustion gases. And so let's look at this gamma, see what that is telling us. So we can think about this process in two parts. Here now we're showing temperature going down to volume. We could look at the volume change, that's mu is constant because no temperature, and then we could look at the delta U in terms of the heat capacity. So the heat capacity is involved in this. And so this is the definition of gamma. It's the ratio of the heat capacities at constant pressure over constant volume. And so that's how we calculate gamma. So let's look at the different types of working fluids, the different types of gases that we could use. And there's really only three types. There's monatomic gas like helium, which only has translations. There's diatomic gases, which have translations and 2 rotations. And then there's nonlinear molecules that have translations and 3 rotations. And we're not getting any energy or heat capacity out of vibrations because they're just too high. Okay, for these small molecules, none of the vibrations are going to be active. The only time you're going to have active vibrations is really big molecules, and those are not going to be they're probably not going to be volatile enough to be a gas that's going to push a piston. So we're only getting our work by the small molecules. So we spray gasoline in there and it burns, but the real thing that's doing the work is the water and the CO2 that are coming off of that and pushing out, and whatever nitrogen is still in there, because we typically have nitrogen and oxygen. So the nitrogen heats up, the oxygen reacts with the fuel and makes CO2 and water, and so we could calculate, if we knew the mix, what gamma would be by adding up all of those different heat capacities. And so if we had 20% oxygen and 5% water and 15% CO2 and such percent of nitrogen, we could add up the CVs for all of those, and then add an R to each one to get the CPs of all of those. So we'd have this composite CP on top and a composite CV on bottom, and that ratio is gamma. And that would help us figure out what this adiabatic line is. So this is the picture that really will explain adiabat versus isotherm. Remember, these are 3 different state variables, and we've just been plotting the P versus V. So on a PV plot, you just see both of these right here. You're looking at them from the side. But there's a third component, the temperature. And so you see here, if we plot that temperature, now you see this 3-dimensional surface. And this is going straight down the hill, what we call the steepest descent, and it's allowing temperature to change. You see? If we wanted to be an isotherm, we have to stay at a particular temperature, and so we have to put heat into the system to keep it on that line. And remember, heat is our cost. And so if we have an adiabatic process in this engine cycle, then we're going to be using less heat on that expansion, and so it'll save us some money. It'll be more efficient. So let's think about this. We have delta U equals Q plus W. Delta U is N, the number of moles, times CV, delta T. And for an adiabat, Q is 0. That's by definition. So you can circle this and say, definition of adiabat. And then the work, we have an external pressure, that piston, and times the change in volume. And so we're going to integrate both sides. We're going to integrate the left side with respect to temperature and the right side with respect to volume. So it's pretty simple. We have that P external is NR over V. It was NRT over V, but we moved T to the other side. And so then this is a pretty simple integral. We end up with NCV, natural log of TA over TB. And then, so that's V final and V initial. And then here we have minus NR ln VA over VB. So N is on both sides. So we're going to cancel that. So we kill N. And we remember that definition of CP. CP was equal to CV plus R. That's a terrible C. Okay. So what is R? R is the difference between CP and CV. So that's what happened here. You see that? So now we have CP minus CB on this side and CV. Let's get all those on the same side. So we're going to move CV over here. And so we just have the temperature side, and then we have this piece in front, and we have the volume side, all these natural logs. And so this piece right here is gamma. This is gamma right here. And this is 1. So gamma minus 1. And whenever you have something times a natural log, you can move it in as an exponent. And then we have logs on both sides, so we can just get rid of those. And so this gamma minus 1 ends up here as an exponent. And so we have the ratio in temperatures for an adiabat. This is the key. These are adiabatic relationships. So the ratio in temperatures is equal to the ratio of volumes raised to this gamma minus 1 power. And the reason we've developed these adiabatic relationships is because we're typically dealing in two-dimensional plots. Okay. We have our state variables table, and we want to know where these points are in the state variables table. So we've got to figure out using 2 of the variables to find the third. And so that's what we need to do. And it depends upon the type of gas, because CV is different for each type of gas. So you've got to know whether it's a monatomic gas, diatomic gas, whether it's a nonlinear molecule, and then that'll help you figure out what these adiabatic relationships are. So you cannot do the Carnot cycle problems without knowing these adiabatic relationships. So this is 1. There's 3, right? There's temperature compared to volume, but there's also temperature compared to pressure and pressure compared to volume. So because you have 3 different pairings of your state variables, you need 3 different relationships. So let's look at the other relationships. So up here, let's say we wanted to get temperature in terms of pressure, or volume. Let's say volume in terms of pressure. Let's do that. So let's just take this top one. And we can see that we can substitute, instead of temperature, that's PV, PA, VA over NAR, and divided by PB, VB over NBR. And the number of moles hasn't changed, so those are gone. R hasn't changed, so that's gone. So this piece right here can go in for this, right? So this right now is PAVA over PBVB. So you see what happened? This piece now goes right here. We just took the temperature ratio out and put in a ratio of pressure and volume. Okay. But now I have volume on the left and volume on the right. And so let's move that over. So if I move this over here, I end up with this ratio of VB over VA. So I have VB over VA raised to a certain power times another one of those. And so if I have x cubed times another x, it becomes x to the fourth. If I had x to the gamma minus 1 times another x, that's x to the gamma minus 1 plus 1. And so the minus 1 and the plus 1 are gone. And so here I have that ratio to the gamma minus 1 times that ratio again, and so that minus 1 disappears. And so this is the relationship between pressure and volume. Notice how temperature's gone. So if I'm in the table and I've got 2 volumes and 1 pressure, I can find the other pressure. And that's how you'll use this equation. So this one is very, very useful. Up here, I've got the temperature and volume relationship. Just from this one, if I wanted to move this to the other side, so if I have, y equals x squared, I could take the square root of both sides, so it would be y to the 1/2 equals x. So I'm just taking the ratio of that, the inverse of this, and moving it to the other side. So that makes sense, hopefully. So from going from the right side over to the left, I just invert it. And so then I have the temperature volume relationship. Don't be confused by these weird exponents. Just remember your rules. And I always try to think, okay, if I have x squared, y equals x squared, I could take the square root of both sides. Then I have y to the 1/2 is equal to x. Okay. Makes sense? Work this. This is nope. You can do this in your pages and prove to yourself that these relationships all work, and just use the ideal gas law. Kind of work your way through it. Hopefully, and that's my goal with these homework pages, is for you to kind of teach yourself at home, try to figure these things out. If you're working on PChem, that counts for your pages. And so sometimes you can make up your own problems to say, I didn't really get that in class, I'm going to do it myself. And do it in your notebook, and that's all legit. So now we have all 3 of our relationships. We have temperature volume, volume in terms of temperature with related relationships of the gamma and gamma minus 1, and then we have pressure and volume. Okay. So let's talk about gamma, all the different kinds of gammas. And there's our 3 relationships up there, simplified. Temperature volume, volume temperature, volume pressure. I don't have the pressure temperature one, but really the one we need is the volume and the pressure, because we're going to be dealing with PV diagrams. And so that's the one that's most useful, is the pressure volume one. So for helium, that ratio of Cp over Cv, remember Cv for helium is just translation, so it's 3/2 R. So we have 3/2 R in the denominator, and you add another 2 for the Cp. So if it's 3/2 R in the bottom, it's 5/2 R in the top. And so then all the R's cancel here, the halves cancel, and we end up with 5/3. So that's gamma, 5/3. For helium. For CO2 or any linear molecule, it's going to be 5/2, because you have 3 translations and 2 rotations. So you have 5 degrees of freedom, so there's 5/2 of an R for the heat capacity constant volume. You add 2 more to get the Cp. And that's where you get 7/5. So that's a really strange ratio, but that's what you get. So the 2's have canceled, the R's have canceled, and gamma is 7/5. And then for water, like steam engines, using water as your working fluid, it's pushing the pistons, you have 6/2 R, 3 translations, 3 rotations. We're not counting the vibrations, they're too high in terms of vibrational temperature. So we just get the 3 translations, 3 rotations, that's Cv. And then you add another 2 to get the Cp, and so you have 4/3 here. So that was 8/6, you divide them both by 2, so 4/3, or 1.33. So those are our those are the only three gammas I've ever seen. Okay. Now you might have a different gamma if you have a mixture of these, like some water and some nitrogen, some oxygen, and so on. So if you're trying to get to be as accurate as possible for like a gasoline engine, it would be something between water and helium. Okay. So here's our Carnot cycle state variables table. It's written a little bit differently. Our points are the rows and our state variables are columns. Okay. So our T hot is A and B. That's an isotherm. The T cold is C and D. So these are isotherms. The dark lines are isotherms and the dashed lines are adiabats. And so we'll pick up here next time and talk about compression ratio and displacement, because that's how we track engines. Right? Think about your automobiles. You have a 6-liter engine or a 3-liter engine, that's the displacement. And then the compression ratio is measured typically with pressure. They'll run it through one cycle and see from the full stroke of that piston how much pressure change it is. So it goes from 1 atmosphere up to some high pressure. You take that ratio and that's your compression ratio. You can also take that pressure compression ratio and convert it to volumes, and that's what we have. We have VC over VA. The big volume over the small volume will give you this compression ratio. And then the delta V is your difference between VC and VA. So you can go to the Trans Am website and see how much a boring job will get you in terms of compression ratio and displacement. And you can put all of these in here. So this is taking delta V, so mark those equations down. They're in the notes. That getting the delta V, which is your displacement, and RC, which is your compression ratio, you can get VA and VC. And that's why I would like to give you these problems. I would like to say, okay, calculate the work and efficiency and everything for a Carnot cycle with this compression ratio and this volume and displacement, because that's how we talk about engines. All right, so I'll see you next time.